previous videos, we have discussed about various types of failure of a bolted connections and the tensile splice. The failure can be due to the bolt, or due to the bearing, or due to the tensile capacity of the plate itself. This can be translated into three design considerations of the connections, which are the shear resistance of the bolt, the bearing resistance of the steel plate, and also the slip resistance caused by the preloaded high-strength bolt. The slip resistance only appears when a bolt class of 8.8 and 10.9 are used, where a preload is applied onto the bolt. This preload causes a compressive load acting onto the steel plate and lead to frictional resistance between the interface of the steel plate. Now we look into the design considerations one by one. First, we need to determine the shear resistance of the bolt. Before that, we need to know the components of the bolt. There is a head, an unthreaded length, and also a threaded length. A typical bolt can appear in two forms, where there are a certain length of unthreaded length and a certain length of threaded, or the entire length of the bolt are threaded. As the threads are normally carved from the unthreaded area, the effective diameter of the bolt for the threaded length after carving are normally smaller than the unthreaded. With that, the effective area of the unthreaded portions and the threaded portions are different. The area of the unthreaded portions are known as the gross cross-sectional area, which is symbol as A, while the area at the threaded regions are known as the tensile stress area, which is termed as AS. In the design of the shear resistance of the bolt, it is important to determine the positions of the shear plane, whether it is at the unthreaded portions or at the threaded portions. This can be normally identified based on the arrangement of the steel plates. In the case that unthreaded portions, the gross cross-sectional area is used. If the shear plane falls within the threaded portions, the AS is used. The equations for a threaded portions and unthreaded portions are given here. For the shear plane fall within the unthreaded portions, the factors are consistently to be 0.6. However, for the threaded portions, the factor will be alpha V, as given in the table 3.4 EC3 part 8. The alpha V are normally 0.5 or 0.6 depending on the bolt class. The FUB here represent the ultimate tensile capacity of the bolt, which can be referred from table 3.1 EC3 part 8. The factor of safety, gamma M2, can be referred from table 2.1 EC3 part 8, which is equals to 1.25. For the AS, you may refer to this table, which vary in accordance to the nominal size of the bolt. As for the gross cross-sectional area, the value would be normally higher than this, which can be calculated from the simple equations to determine the area of a circle, namely pi r square. The gross cross-sectional area can be easily computed based on the diameter of the bolt, And with that, we are able to determine the shear resistance of the bolt. Next, we need to look into the setup of the connections. The resistance of the connections due to the bolt will be governed by the number of the shear plate. Next, we look into the bearing resistance of the steel plate. For a tensile splice being subjected to the tensile load, one of the plate is moving to the other side while another is moving to the other side. The contact between the steel plate and the bolt will be the bearing area. Based on the principle of static equilibrium, the total resistance by the bearing load will be equivalent to the total tensile force acting on the plate. And it is assumed that the bearing area remains in the plane form. To determine the bearing resistance of the steel plate, this equation is to be used. The dt here represents the bearing area, which is effectively the width of the bolt and the thickness of the plate. With that, the bearing area effective regions will be here. The Fu here represents the tensile capacity ultimate for the steel plate. It is not the tensile capacity of the bolt, because the bearing resistance is all about the steel plate. The factor of safety gamma M2 will be equals to 1.25, and we have two factors here, K1 and alpha B. The K1 and alpha B here is distinguished by the positions of the bolt. It's either at the end or the edge or the inner bolt. Taking this as an example, these two will be the end bolts, and this will be the edge bolt, and this will also be the edge bolt. In case that there is another series of bolts here, the bolt positions here will be the inner bolt. The equations to determine the alpha B and K1s are given here. It is normally in the functions of the geometrical arrangements of the bolt in relative to the diameter of the bolt hole and some constant numbers. For the alpha B, there is an consideration of the ultimate tensile capacity of the bolt in relative to the ultimate capacity of the plate. The minimum values are being adopted to yield the smallest bearing resistance for conservative considerations. For a more precise calculations, you need to check for the bearing resistance for every single bolt depending on whether they are the end bolt, edge bolts or the inner bolts. In the case that you have numerous bolts, especially at least 3 layers of bolts in the series, there will be distinctions between the end bolt, edge bolt and also the inner bolt. The calculations will become slightly lengthy and tedious. For simplicity, you may always go for the smallest value so that it yields the lowest bearing resistance possible among the bolt group and to be multiplied with the number of bolts. This shall give you a slightly more conservative estimations of the bearing resistance of the steel plate. Next, we look into the slip resistance design. The relevant equations are given here. The factor of safety used is gamma M3, which if it is used to determine the resistance at the ultimate limit state and surface limit states will be different, which are 1.25 and 1.1 respectively. FPC here represents the shear resistance of the boat, which is assumed to be 70% of the ultimate capacity of the boat to be multiplied with the effective area of the treated regions of the boat. There are three factors here: K1, eta, and mu. K1 can be obtained from table 3.6, which is normally assumed to be 1.0. And the eta here represents the numbers of frictional interfaces. This is determined based on the setup of the tensile splice. And the mu here represents the slip factor, which can be referred from table 3.7, EC3 part 8. The details for the K1s and the mu are listed in the table here. And the slip factor varies in accordance to the surface class, from class A to class D. The descriptions of the relevant classes are given here. In general, surface class A are normally rough and give a higher degree of frictional coefficients, while surface class D are normally smooth and the slip resistance are normally low, as represented by the coefficients of frictions. Based on the components within the equation here, you will know that the slip resistance are calculated on basis of the treated area of the boat. The bearing resistance is calculated based on the steel plate, while the shear resistance is calculated based on the property of the boat. What you can see here, there are differences in terms of the usage of the property between the boat and the steel plate. You should use the property appropriately.